Chapter 25 Atoms and Radioactivity. Hello everyone, Dennis here. This video is brought to you by Ace with Dennis. Now, learning can be smart, not hard. Don't forget to subscribe and press the bell notification button to stop missing out free lessons from me. In this video, you are going to learn atomic particles, isotopes, ionization, alpha, beta, and gamma radiation, radioactive decay, half-life, nuclear fission, nuclear reactors, nuclear fusion, and usage of radioactivity. Let's begin the lesson with simple model of an atom. We should know that everything is made of atoms. A simple model of an atom can explain the basic ideas how an atom works. An atom is made out of three types of smaller particles, which are neutrons, protons, and electrons. Protons and neutrons make up nucleus, the center of the atom. So here is the nucleus. Electrons travel around the nucleus in their own orbits at high speed. So here is the orbits of the electrons. Neutrons has no charge. Protons have positive charge, while electrons have equal but negative charge. A neutral atom has the same number of electrons and protons. Electrons are held in orbit by the force of attraction between opposite charges. Protons and neutrons are bound tightly together in the nucleus by strong nuclear force. Next, let's discuss elements and atomic numbers. All materials are made from substances called elements. There are 118 known elements which are recorded in a periodic table. So here is how a periodic table looks like. And there are some important information we can get from this table. So let's look at the key here. Each element has different number of protons in its atom. So the number at the top of the atomic symbol is the atomic number. For example, hydrogen has atomic number of 1. So what is an atomic number? An atomic number, also known as proton number, tells us the number of protons in the atom. Since a neutral atom has the same number of protons and electrons, atomic number also tells us the number of electrons in the atom. Let's take a few more examples here. So the first one is lithium. So from the periodic table, the symbol for lithium is Li and the atomic number is 3. Next, calcium, symbol is Ca and atomic number is 20. Next, mercury, symbol is Hg and the atomic number is 80. Followed by carbon, symbol is C and atomic number is 6. Let's take one more element, O, which is oxygen, symbol O and atomic number is 8. Next, let us discuss isotopes and mass number. So, what are isotopes? Isotopes are atoms that are the same element but have different number of neutrons. They have identical chemical properties, but they have different masses. So, what is a mass number? Mass number tells us the total number of protons and neutrons. Since isotopes have the same number of protons but different number of neutrons, hence isotopes have the same atomic number, which is number of protons, and different mass number. So here's an example. This symbol Li is lithium. The mass number is 7 and the atomic number is 3. So we know that mass number is proton plus neutron, and atomic number tells us the number of protons only. Hence, the number of neutrons for this isotope is 7 minus 3, which is 4. Hence, to illustrate, here are the 4 neutrons with 3 protons. Another isotope for lithium is this, where the number of protons is 3 and the number of neutrons will be 6 minus 3, which is equals 3. So here is the illustration. We have 3 neutrons and 3 protons. Next, let's see more examples of isotopes. The first element example is hydrogen, and the first isotope is hydrogen 1. From here, we can see that the mass number is 1 and the atomic number is 1. Hence, the number of protons is 1, number of electrons is 1, and the number of neutrons is 0. To draw the model, this isotope has 1 proton but no neutrons and is orbited by 1 electron. The second isotope is hydrogen 2. From here, we can see that the mass number is 2 and the atomic number is 1. Hence, number of protons is 1, number of electrons is 1, and the number of neutrons is 1. So to draw it in model, it has 1 proton, 1 neutron, and 1 electrons orbiting the nucleus. Next element is oxygen. The first isotope is oxygen 16, where from here we can see that the mass number is 16 and atomic number is 8, which means the number of protons is 8, number of electrons is 8, and the number of neutrons is 8. So to draw the model, this isotope has 8 neutrons and 8 protons in the nucleus, and it is orbited by 8 electrons. The second isotope is oxygen 18, where the mass number is 18 and the atomic number is 8. So from here, we can see that the number of protons is 8, number of electrons is 8, but the number of neutrons is 10. So to draw the model, in the nucleus there are 10 neutrons, 8 protons, and this nucleus is orbited by 8 electrons. The next example is carbon. So carbon has 3 isotopes, which are carbon 12, carbon 13, and carbon 14. For carbon 12, the mass number is 12 and the atomic number is 6, which means the number of protons is 6, the number of electrons is 6, and the number of neutrons is 6 as well. So the model will be, there are 6 neutrons, 6 protons in the nucleus, and this nucleus is orbited by 6 electrons. For carbon 13, the mass number is 13 and the atomic number is 6, which means number of protons is 6, number of electrons is 6, and number of neutrons is 7. Hence, there are 7 neutrons and 6 protons in the nucleus. This nucleus is orbited by 6 electrons. Next, carbon 14, the mass number is 14 and the atomic number is 6, which means it has 6 protons, 6 electrons, and 8 neutrons. So for the model, it has 8 neutrons and 6 protons in the neutron, and this nucleus is orbited by 6 electrons. Next, let's discuss about the concept of electron shells. Electrons orbit the nucleus at certain fixed level only. These levels are called shells. Each shell can hold certain number of electrons only. The maximum number of electrons per shell in order of increasing shell number from 1 to 4 was said to be respectively 2, 8, 8, and 18. Okay, so what does it mean? Let's see a few examples so that you can get the idea. We'll see the first model of hydrogen 2. As you can see, there is one electron orbiting the nucleus. Hence, the electron configuration will be 1. Next, the second model is the oxygen 18. So as you can see from here, there are two shells for this model, where the first shell has 2 electrons and the second shell has 8 electrons. So we write the electron configuration as 2, 8. The next example here, so this is carbon 14. As you can see, there are also 2 shells where the first shell has 2 electrons and the second shell has 4 electrons. So the electron configuration will be 2, 4. Now, let us discuss nuclear radiation part 1. But before that, let's recap the concept of isotopes. Isotopes are atoms that have the same atomic number but different mass numbers. In other words, atoms of the same number of protons but different number of neutrons. Since they have the same atomic number or number of protons, they have the same element. Hence, they have identical chemical properties. But here's the problem. Some materials contain atoms with unstable nuclei. An unstable nucleus can disintegrate and shoots out a tiny particle and sometimes a burst of wave energy. These tiny particles and waves radiate from the nucleus. Hence, they are called nuclear radiation. Radioactive materials are materials that emit nuclear radiation. The disintegration of nucleus is called radioactive decay. We often say some materials in power plants, which is man-made, are highly radioactive. However, nuclear radiation also comes from natural sources. Certain isotopes of the same element are radioactive. So let's see the concept here. For isotopes, they are stable nuclei, for example, carbon-12 and carbon-13. For unstable nuclei, we have carbon-14. And all these can be found in air, plants, and animals. Another example for stable nuclei is potassium-30. Unstable nuclei is potassium-40, and they can be found in rocks, plants, and seawater. One more very common or popular unstable nuclei are uranium-234, uranium-235, and uranium-238. They can be found in rocks. Now let's discuss ionizing radiation. An atom is neutral when it has the same number of protons and electrons. It becomes ionized or ion when it either loses electrons or gains electrons. For example, so this is a model of hydrogen 2. So when it loses one electron, it becomes positively charged. We can write as H+. Another example, so this is a model of oxygen 18. Now, 2 electrons is attracted towards the nucleus and it becomes negatively charged. We can write as O2 negative. Nuclear radiation can remove electrons from atoms in its path. Hence, nuclear radiation has ionizing effect. Ultraviolet and X-rays are other forms of ionizing radiation. So here are some effects of ionization. First, ionized gas will conduct an electric current. Ionization can damage or destroy cells or living things. There are three main types of nuclear radiation. The first type is alpha particles, which are positive charges. Second type is beta particles, which are negative charges. And the third type is gamma rays, which are neutral. Now, let us compare between protons, neutrons, and electrons in two aspects, a mass and charge. So, a proton has a mass of 1.673 times 10 to the power negative 27 kilograms. A neutron has a mass of 1.675 times 10 to the power negative 27 kilograms, and an electron has a mass of 9.109 times 10 to the power negative 31 kilograms. If we compare the masses in kilograms, it will be very difficult for us to compare because the number is very small. Hence, we can compare with relative mass. Let us assign the mass of an electron as 1 unit. If we compare the mass of electron and neutron, we will find that the relative mass for neutron is 1838.68. If we compare proton-electron, then the relative mass for proton will be 1836.15. So from this comparison, we can make several conclusions here. The first one is a proton and a neutron have similar or almost the same mass. The mass of a proton and neutron are about 1800 times larger than an electron's. Hence, the mass of an electron is often negligible. Next, we also compare protons, neutrons, and electrons in terms of charge. So, a proton has a charge of positive 1.6 times 10 to the power negative 19 coulomb. For neutron, it has 0 coulomb charge. For electron, it has negative 1.6 times 10 to the power negative 19 coulomb. So, if you compare the relative charge, a proton has positive 1, neutron is 0, and electron is negative 1. So from here, we can make conclusion that a proton and an electron has equal and opposite charge, while a neutron has no charge, hence it is neutral. Next, let's discuss comparison between alpha particles, beta particles, and gamma rays. So, for alpha particle, the composition is 2 protons and 2 neutrons. For beta particle, it has 1 electron. And for gamma ray, it has electromagnetic wave. So the relative charge for alpha particle is positive 2 since it has 2 protons, while for beta particle, it is negative 1 since it has 1 electron, and for gamma ray, as it does not have any particle, hence the relative charge is 0. Next, we compare the relative mass. For beta particle, since it has 1 electron, then the relative mass is 1. For alpha particle, since it has 2 protons and 2 neutrons and they have very similar mass, hence the relative mass will be 4 times 1800, which is about 7200. So from here, you can see that the relative mass for alpha particle is very high compared to beta particle. While for gamma ray, again, since it has no particle, then it has no mass. For the speed, gamma ray can travel at the speed of light, while alpha particle, it can travel 0.1 times of speed of light as it has high relative mass. On the other hand, for beta particle, it has 0.9 times the speed of light. For ionizing effect, since alpha particle has relative charge of positive 2, hence it has strong ionizing effect. For beta particle, it has relative charge of -1, hence it has weak ionizing effect. For gamma ray, it is neutral, hence it is very weak ionizing effect. And the next comparison is, can they be deflected by magnetic and electric fields? For alpha particle, it is yes, and for beta particle, it is yes as well, as both of them have charges. So for gamma ray, since it is neutral, then it does not be deflected by magnetic and electric fields. Okay, now let's see how we can determine how alpha particle, how these alpha particles, beta particles, and gamma ray affected by magnetic field. So let's assume these three alpha, beta, and gamma radiation moving on a straight line. And since gamma ray is not affected or deflected by magnetic and electric field, it will continue to go in a straight line. So next, to determine how alpha and beta particles are deflected by magnetic field, so we use the Fleming's left-hand rule, where our index finger will point from north to south of the magnetic field. Our middle finger will point in the direction of the conventional current, and the thumb will point the force current F. So now for alpha particle, this will be the direction of our index finger, which points from north to south of the magnetic field. This will be our middle finger, which is pointing the conventional current direction. As alpha particle is positive charge, hence the index finger will point at the same direction of this alpha particle. So our thumb will automatically point outwards. So which tells us this is the force direction, which means alpha particle will be deflected in the outwards direction. We'll do the similar process for beta particle, where this will be the direction of our index finger pointing from north to south. This will be the direction of our middle finger pointing the conventional current direction, as beta particle is negative charge. Hence, the conventional current will be opposite direction. And our thumb will automatically point downwards. So which means this will be the direction of the beta particle, which is deflected downwards. Here are a few observations and explanation from this activity. So first, gamma wave moves in a straight line. The reason is because gamma wave is uncharged. It is the least ionizing. And alpha beam is a flow of positively charged particles. It is equivalent to the flow of conventional current. Hence, when we point our middle finger, which is pointing the direction of conventional current, so it will be pointing the same direction of this gamma particle. A beta beam is a flow of negatively charged particles. It is equivalent to the opposite flow of conventional current. Hence, we point our middle finger in the opposite direction of this beta particle. Beta particles are much lighter, which is less momentum than alpha particle. Hence, beta particles travel much faster than alpha particle, and therefore beta particles deflected more compared to alpha particles. So you can use this explanation to answer the question if they ask you why we can see that beta particle deflects more compared to alpha particle, or why beta particle travels faster than alpha particle. Next, we also want to observe how alpha particle, beta particles, and gamma ray deflects when they pass through electric fields. So let's say these three are passing through the electric field. For gamma ray, it will travel in a straight line. For alpha particles, since they are positive charge, you will be attracted towards the negative plates. For beta particles, since they are negative charge, they will be deflected towards the positive plates of the electric field. So the observation and explanation here are gamma waves move in a straight line. Gamma waves is uncharged and not affected by electric field. For alpha particles being positively charged, they are deflected towards the negative plates. For beta particles being negatively charged, they are deflected towards positive plates. Beta particles are deflected more compared to alpha particles because they are lighter, which has less momentum and travel in faster speed compared to alpha particles. Next, we also want to compare the penetration effect. For alpha particle, it is not very penetrating. For beta particle, it is penetrating, and for gamma ray, it is very penetrating. So, how these radiations can be stopped by? For alpha particle, it can be stopped by a thick sheet of paper, skin, or a few centimeters of air. For beta particle, it can be stopped by a few millimeters of aluminum or other metal. For gamma ray, it can be completely stopped, but the intensity can be reduced by lead or thick concrete. Now let's observe how these radiations can be stopped or penetrating. So imagine if they are traveling on a straight line, and if I place a thick sheet of paper, alpha particle will be stopped, while beta particles and gamma ray will continue to travel on a straight line. And if I place an aluminum sheet here, the beta particle will be stopped, but for gamma ray, it will continue to travel on a straight line. And if you place a thick lead here, the gamma ray will still continue to travel straight, but with less intensity. Alright, let's put everything together into a table, the comparison between alpha particles, beta particles, and gamma rays. So the composition of alpha particle is 2 protons and 2 neutrons, which is identical to a nucleus of helium-14. For beta particles, it has 1 electron, and for gamma ray, it is electromagnetic wave. The relative charge for alpha particle is positive 2, as it has 2 protons. For beta particles, it is negative 1, since it has 1 electron, and for gamma ray, since it has no particle, hence the relative charge is 0. Next, relative mass for beta particles, it is 1, and for alpha particle, it is 4 times 1800 because it has 2 protons and 2 neutrons, so the relative mass is about 7200, which is very high compared to beta. For gamma ray, it has no mass. For the speed, gamma rays can travel at the speed of light. Alpha particles can travel at 0.1 times of speed of light, while beta particles can travel at 0.9 times of speed of light. Ionizing effect for alpha particles is strong, beta particles is weak, gamma rays is very weak. Can be deflected by magnetic and electric fields. Alpha particle is yes, beta particles yes, gamma rays no. Penetration effect. Alpha particles is not very penetrating, beta particles are penetrating, and gamma rays are very penetrating. Stopped by. Alpha particles can be stopped by a thick sheet of paper, skin, or a few centimeters of air. For beta particles, it can be stopped by a few millimeters of aluminum or other metal, and for gamma rays, it can be completely stopped. But intensity can be reduced by lead or thick concrete. Now we enter the topic nuclear radiation part 2. First, let's talk about dangers of radiation. How dangerous is radiation? It causes damage or destroy living cells. Organs in the body cannot work properly, and damaged cells will grow abnormally and cause cancer. There are two factors that can increase the risk. First, the intensity of the radiation. Second, the time of exposure. Next, the problem of radioactive gas and dust. Radioactive gas and dust can be taken easily into the body with air, food, or drink. Once absorbed, it is difficult to be removed. It can cause cell damage deep in the body. Take note that there is much less risk from radioactive sources outside the body. Now, let's discuss a few questions related to the dangers of radiation. First question. Among alpha radiation, beta radiation, and gamma radiation, which one is or which ones are the most harmful to our body? The answer is beta radiation and gamma radiation. The reason is because they can penetrate to internal organs. On the other hand, alpha particles can be stopped by the skin. Second question. Among alpha radiation, beta radiation, and gamma radiation, which one is or which ones are the most damaging to the cells? The answer is alpha particles. The reason is because alpha particles are the most highly ionized compared to beta and gamma. Here are a few safety measures that we can take to minimize the danger of radiation. First, we minimize the time of exposure to radiation. Second, we keep a big distance from the radioactive source as possible. Third, we can use shielding against radiation. For example, we can wear protective clothing made from dense materials, such as lead. Nuclear power stations and laboratories are well shielded to prevent radioactive radiation from leaking out. Fourth, radioactive waste must be disposed carefully. We handle it remotely after being thoroughly cooled and bury it underground in sealed drums. Do you know that radioactive radiation is around us all the time, even now? This is called the background radiation. The small amount of radiation around us all the time due to radioactive materials in the environment. Here are a few sources. Number 1. The main source is radon gas or radon-222 from the ground. Radiation seeps out of rocks, especially granite. Number 2. Ground and buildings. Number 3. From medical equipment and devices such as X-rays. Number 4. Even our food and drinks are the sources of radiation. Number 5. Cosmic rays from space. Number 6. Others such as nuclear test fallout, nuclear power stations, nuclear waste, and etc. To overcome the risk from background radiation, houses may need extra underground ventilation or steel floor to stop the radiations from entering. Now we'll discuss several devices that can detect radiation. The first device is Geiger-Müller or GM tube, which is used to detect alpha, beta, and gamma radiation. Now let's talk about the structure of this GM tube. So this is a GM tube where it is made out of metal tube, and inside the tube is filled with low pressure gas, which is argon. The metal tube is connected to the negative terminal of 450 volt DC supply, and hence this connection is cathode, which causes the metal tube to be negatively charged. In the middle of the metal tube is a central wire. This central wire is connected to the positive terminal of the 450 volt DC supply, hence it is called the anode, and the central wire is positively charged. The rate meter or scaler is connected here to count the number of radiations detected. At this end of the metal tube is thin mica window where the radioactive radiations entered the GM tube. Now, how does GM tube work? When a radioactive particle, whether alpha, beta, or gamma radiation, enters the window, it takes away an electron from argon atom. The electron is attracted to the central wire at high speed due to high voltage, which is positive 450 volts. The high-speed electron hits other electrons from other argon atoms, causing an avalanche. One single incoming radioactive particle will cause many electrons to arrive at the central wire, creating a pulse of current which can be amplified and counted. GM tube can be connected to a few devices. Number 1. A rate meter. The reading given from a rate meter is in counts per second. Example, 50 counts per second, which means the GM tube detects 50 radioactive particles entering the tube every second. Number 2. A scaler. This apparatus gives the total number of particles or bursts of gamma radiation detected by the tube. Number 3. An amplifier and loudspeaker. The amplifier amplifies the pulse so that the loudspeaker makes a click sound when each particle or burst of gamma radiation is detected. When the radiation from radioactive source is measured, the reading always includes any background radiation present. To obtain an accurate measurement, an average reading for the background radiation alone must be found and subtracted from the total. Another device that can be used to detect radioactive radiation is cloud chamber. It can detect alpha, beta, and gamma radiations. This is a cloud chamber. At the top of the cloud chamber is closed with plastic lid. Below the plastic lid is a layer of pad soaked in alcohol. This pad is to supply alcohol vapor in the chamber. Hence, inside the chamber is filled with condensed alcohol vapor. This alcohol vapor is to form liquid droplets around the ionized molecule. At the bottom of this cloud chamber is a layer of cooling unit, such as dry ice. It cools alcohol vapor until it is saturated. A radioactive source is connected at this end, which produces radiation and causes ionization of vapor. A light bulb is shown inside the cloud chamber so that the tracks of radiation can be observed easily. There are a few track patterns can be observed in the cloud chamber which tell us which type of radiation is detected. For example, this pattern, as you can see, we have straight lines. So this track pattern is alpha particle tracks. It is thin and straight. This is because occasional deflection due to collision of the alpha particle with air molecules. The second track pattern is in this manner, which tells us it is beta particle tracks. The pattern is thin and crooked. Particles cause much less ionization. Since particles are much lighter, they are continuously being pushed off by nearby air molecules. The third pattern is in this manner, which tells us gamma ray. Gamma ray don't produce tracks. Tracks observed are caused by electrons which absorb energy from photons and have escaped from atoms. Let's summarize the types of detectors in a table. So the first detector is the GM tube with rate meter. GM tube can detect alpha particles, beta particles, and gamma rays. The observation is the rate meter shows a count rate higher than the background count. The second detector is the cloud chamber, which can detect alpha particles, beta particles, and gamma rays. The observation is tracks with specific characteristics are formed in the cloud chamber, which we have discussed in the previous page. Next detector is the photographic batch, which can detect beta particles and gamma rays. The observation is the darkening of the photographic plate in the batch. And the next detector is the spark counter, which it can detect alpha particles. The observation is sparks are seen and heard between the wire gauze and the wire below it. Next, the topic is radioactive decay, part 1. We will learn how radioactive decay works. We start with the introduction. First, if an isotope is radioactive, it has an unstable arrangement of neutrons and protons in its nucleus. The isotope will emit an alpha or beta particle to make it become more stable. However, this will change the number of protons and neutrons in the nucleus. The isotope will become different element after the change. The original nucleus is called parent nucleus, and the new nucleus form is called the daughter nucleus. The daughter nucleus and any emitted particles are the decay products. Alpha decay. As we learned previously, alpha particle consists of 2 protons and 2 neutrons. This is identical to a nucleus of a helium-4 atom. Hence, we can also write alpha particle as helium-4 atom. And here is the notation for alpha particle with the mass number of 4 and atomic number of 2, which means we have 2 protons and 2 neutrons. So same as the atom for helium, which also have the mass number of 4 and atomic number of 2, which means it has 2 protons and 2 neutrons. Let's look at a few examples of alpha decay. So here is the first example. Uranium-238 as the parent nucleus decays and produces thorium-234, which is the daughter nucleus, and alpha particle. Thorium-234 and alpha particle are the decay product. Here is a second example of alpha decay. Thorium-230 decays and produces radium-226 and alpha particle. One more example is radium-226 decays and produces radium-222 and alpha particle. So in general, in alpha decay, the parent nucleus of mass number m and atomic number a decays and produces daughter nucleus with the mass number of m-4 and the atomic number a-2 and alpha particle. So the parent m and daughter m-4 with alpha particle. The second decay is beta decay. So the question is, what is beta decay? Beta decay is one type of radioactive decay where a proton is transformed into a neutron or vice versa inside the nucleus of the radioactive sample. This is because certain radioactive atoms have unstable ratio of neutrons to protons. The number of neutrons and the number of protons in the atom need to change so that the atom becomes stable. There are two types of beta decay. Number 1, beta plus decay, and number 2, beta minus decay. In O-level syllabus, we will focus on beta minus decay, but over here I will explain both so that you can have a clearer picture about beta decay. In beta plus decay, the proton disintegrates to yield a neutron. This causes a decrease in the atomic number of the radioactive sample. The nucleus experiences a loss of one proton but gains a neutron. Beta plus decay uses a positron and a neutrino. And here is the chemical equation of beta plus decay. For a proton, which is positive charge, after beta plus decay, it produces neutron, which is no charge, a positron, and a neutrino. A positron is the antimatter equivalent of an electron. It has all the same aspect of an electron except that it has a positive charge. A neutrino's behavior is the same as the anti-neutrinos, which we will discuss in beta minus decay. On the other hand, beta minus decay is the opposite of beta plus decay, where a neutron is transformed to yield a proton. This causes an increase in atomic number of the radioactive sample. The nucleus experiences a loss of one neutron but gains a proton. Beta minus decay uses an electron and an anti-neutrino. Here is the chemical equation of beta minus decay. A neutron, after decay, uses a proton, an electron, and an anti-neutrino. Anti-neutrino is the antimatter counterpart of neutrino. Both of them are neutral particles with negligible mass. Let's take a look of the masses here. Electron mass is about 9.109 times 10 to the power of negative 31 kilograms. Neutrino mass is less than 2.14 times 10 to the power of negative 37 kilograms, and anti-neutrino mass is also about less than 2.14 times 10 to the power of negative 37 kilograms. As you can see the comparison here, both neutrino and anti-neutrino is millions of times lighter than an electron. Hence, their masses are negligible. Let's take a look of a few examples of beta plus decay. The first example is carbon-10, which is the parent nucleus. After decay, it produces boron-10, which is the daughter nucleus, a positron, and a neutrino. A positron and a neutrino is the beta particle, while boron-10, positron, and neutrino are the decay product. The second example of beta plus decay is magnesium-23. After decay, it produces sodium-23, a positron, and a neutrino. In general, here is the chemical equation of beta plus decay. A parent nucleus decays and produces daughter nucleus, a positron, and a neutrino. The summary of beta plus decay is a proton is transformed into neutron. Mass number does not change. Atomic number decreases by 1. A new element is formed, which is the daughter nucleus with an atomic number 1 less than parent. The bottom numbers, which is the atomic numbers, are balanced on both sides of the equations. Beta particles produced are positron and neutrino. Now, we also want to take a look of a few examples of beta minus decay. The first example is carbon-14, which is the parent nucleus. After decay, it produces nitrogen-14, which is the daughter nucleus, an electron, and an anti-neutrino. The electron and anti-neutrino are the beta particles, while nitrogen-14, electron, and anti-neutrino are the decay product. Next, the second example for beta minus decay is cobalt-60, which is the parent nucleus. After decay, it produces nickel-60, an electron, and an anti-neutrino. In general, here is the chemical equation of beta minus decay, which start with the parent nucleus. After decay, it produces the daughter nucleus, an electron, and an anti-neutrino. The summary of beta minus decay is a neutron is transformed into proton. Mass number does not change. Atomic number increases by 1 because a neutron is transformed into a proton. A new element is formed, which is the daughter nucleus with an atomic number 1 more than the parent. The bottom numbers, which is the atomic numbers, are balanced on both sides of the equation. Beta particles produced are electron and anti-neutrino. The third radiation is gamma rays or gamma radiation. Gamma rays or gamma radiation is high-energy electromagnetic radiation emitted by an atomic nucleus undergoing radioactive decay. The emission of an alpha or beta particle from a nucleus leaves the protons and neutrons in an excited arrangement. As the protons and neutrons rearrange to become more stable, they lose energy. This energy loss is emitted as a burst of gamma radiation. Gamma ray has no charge. It does not change the mass number and the atomic number of the element it is emitted from. We are now entering radioactive decay, part 2. Here are a few pointers to know about radioactive decay. Number 1. Radioactive decay happens spontaneously or all by itself and at random. Number 2. It is not predictable. We can't predict when a particular nucleus will disintegrate and in which direction the particle will emit. Number 3. Radioactive decay is not affected by pressure, temperature, and chemical change. Number 4. The more unstable a certain type of nucleus, the higher the rate of decay. Next, let's discuss half-life, T-half. So this is a very important quantity in radioactive decay. So what is half-life? It is the time taken for half the nuclei of a radioactive isotope present in any given sample to decay. Example, Cobalt-60 has half-life of 5.27 years. Now, here is how it looks like on a graph. One half-life means 5.27 years. So when the number of half-lives is 0, Cobalt-60 has 100% remaining. So when it completes one half-life, then the remaining is 50%. Followed by second half-life, and the remaining will be 25%. Go to the third half-life, you will remain 12.5%. The fourth half-life remain will be 6.25%, and the fifth half-life, the remaining will be 3.125%. We can join these points together and form a curve. Okay, so now in terms of the mass wise, let's start with 20 grams. Initially, it has 20 grams. After one half-life, the mass becomes 10 grams. After two half-lives, it becomes 5 grams. The third half-life, it remains 2.5 grams. Fourth half-life, 1.25 grams. And the fifth half-life, 0.625 grams. Okay, so this is how we calculate how much remains. So the formula will be 1 over 2 to the power of n times with the initial amount. Here are examples of some radioactive isotopes and their half-lives. We have boron 12, half-life is 0.02 seconds, radon 220, half-life is 52 seconds, iodine 128, half-life is 25 minutes, and so on. And look at the last row, uranium 238, it has half-life of 4.5 times 10 to the power of 9 years. As you can see, when isotopes have smaller mass number, it has short half-life. When it has very large mass number, then it has a very long half-life. Now, let's look at this example. A sample of technetium-99m or Tc-99m originally contained 80 grams, and after 24 hours, only 5 grams of the original Tc-99m remain. What is the half-life of Tc-99m? Here is the solution. First, we apply this formula, how much remains equals 1 over 2 to the power n times initial amount. So for this case, we apply the values given. 5 grams remain equals 1 over 2 to the power n times initial amount, which is 80 grams. Then we solve this equation. 2 to the power n equals 80 over 5, which means 2 to the power n equals 16, and n equals 4 half-lives. Hence, in 24 hours, it completes 4 half-lives. So now to calculate 1 half-life, it is equals 24 divided by 4, which is 6 hours. The next important quantity is activity, which is related to half-life. So what is activity? It is the average number of disintegrations per second in a radioactive sample. The SI unit is becquerel, BQ. So for example, a particular radioactive sample has an activity of 100 BQ, which means there are 100 nuclei disintegrating every second in this radioactive sample. Activity is proportional to the number of undecayed nuclei. Hence, activity also halves every half-life. So for example, 20 grams of fluorine-20, where the half-life is 11 seconds, and specific activity equals 1.87 times 10 to the power 27 BQ per grams. So from this information, we can calculate the activity for fluorine-20. So it will be the specific activity multiplied with the initial mass. So for this case, 1.87 times 10 to the power 27 times 20. we'll get the activity is 3.74 times 10 to the power of 28 BQ. And now we can start to plot the graph where the y-axis is the fluorine-20 activity in the unit of 10 to the power of 27 BQ. So one half-life is 11 seconds. At the beginning, which is 0 half-life, the activity is 37.4 times 10 to the power of 27 BQ, or the mass is 20 grams. After one half-life, then the activity will be 18.7 times 10 to the power of 27 BQ, or the mass is 10 grams. Then after two half-lives, the activity remains 9.35 times 10 to the power of 27 BQ, and the mass is 5 grams. The third half-life, so divided by 2, again we get 4.675 times 10 to the power of 27 BQ, and the mass is 2.5 grams. The fourth half-life, we have 2.3375 times 10 to the power of 27 BQ, and the mass is 1.25 grams. And the fifth half-life, the activity is 1.16875 times 10 to the power of 27 BQ, and the mass is 0.25625 grams. And we can join all these points together when we get a curve. So from here, we can form the formula to calculate the activity remains, which is equals to 1 over 2 to the power of n times the initial activity. So based on the previous discussion, half-life also can be defined as the time taken for the activity of any given sample to fall to half of its original value. Let's look at this example. The isotope iodine-131 is used in nuclear medicine for thyroid treatment, has a half-life of 8 days. If the initial activity of a sample of iodine-131 is 500 MeBq, how much activity will be present in 14 days? So here's the solution. First, we need to calculate the number of half-lives. So for this case, we take 40 days divided by 8 days, which we have 5 half-lives. Then we apply this formula. Activity remains equals 1 over 2 to the power n times initial activity. So we substitute the values that we have. So 1 over 2 to the power 5 times 500. And we get 15.625 MeBq. This is the activity against time graph that we have discussed in a previous page. In reality, to obtain the graph from the left, GM tube is used to detect the particles emitted by the sample. The number of counts per second shown in rate meter is adjusted to allow for background radiation. The adjusted figure is proportional to the activity. However, not all emitted particles are detected. Hence, the adjusted figure is not equal to the activity. Remember that radioactive decay is a random process. In practice, the curve is a best fit of the points which vary irregularly. So, in reality, this curve looks like this, where we have many points at the above of the curve and many points below the curve. Next, let's discuss the stability of the nucleus. The ratio of the number of neutrons to protons determines the stability of a nucleus. Some proportions of neutrons to protons in a nucleus are more stable than others. The graph of the number of neutrons against the number of protons can be plotted. So, the x-axis is the proton number and the y-axis is the number of neutrons. This red line is the stability line. Stable isotopes lie along the stability line. The isotopes above the stability line has too many neutrons to be stable. Hence, they decay by beta minus emission to reduce the number of neutrons. On the other hand, isotopes below the stability line has too few neutrons to be stable. So they decay by beta plus or positron emission to increase the number of neutrons. The heaviest isotopes, which is proton numbers greater than 83, decay by alpha emission. Alright, now let's recap with what we have learned so far. Atoms of the same element have the same number of protons in the nucleus. When the number of protons is changed, an atom with completely different element is formed. Isotopes are elements of the same type in different versions. The number of protons in a nucleus is the same, but the number of neutrons is different for isotopes that are the same element. The number of neutrons in the nucleus is different for isotopes that are the same element. Radioactive isotopes have unstable nuclei. When these isotopes decay, they will emit one or more particles and sometimes gamma radiation. We are entering the last part of the chapter, nuclear energy. We will start with nuclear fission. Nuclear fission is the process of splitting a nucleus. A very popular example of nuclear fission is uranium-235. When a thermal, slow-moving neutron strikes uranium-235 nucleus, the nucleus splits into two daughter nuclei and 2 or 3 neutrons, releasing energy in the process, as shown in this animation. The released neutrons then can induce further fission events in a chain reaction by striking other uranium-235 nuclei. After understanding how nuclear fission process works, we apply the knowledge to generate nuclear energy. We start with learning the structure of nuclear reactor. So here is how it looks like. This is steel pressure vessel. Inside this steel pressure vessel, we have nuclear fuel in core. In between this nuclear fuel in core, we have control rods. Cool water will flow into the steel pressure vessel, cool down the nuclear fuel in core, and flow out as hot water. So here are the functions of the structure. We start with the control rods, usually made of boron or cadmium to absorb neutrons. They are raised or lowered to control the number of neutrons and hence control the rate of reaction. Second, the moderator. The moderator usually is water or graphite. It collides with neutrons so that they are moving slow enough to be absorbed by another uranium-235 nucleus. Then we have the coolant, where water acts as the coolant. It cools down the system and prevents it from overheating. Next, the steel pressure vessel. It is thick enough to withstand high pressures and temperatures. It absorbs some radiations. Next, we'll learn the nuclear reactor system and see how it generates electricity. So we start with the reactor core. So the hot water is pumped up and being cooled down before it is flowed back to the reactor core and repeat the process. So how it is cooled down? So the hot water is flowed into another container which has cool water, and this cool water will absorb the heat and turn into steam. This steam will be flow out to turn a steam turbine. This steam turbine is connected to electric generator to generate electricity. Then the steam flow back into another container, which is called the condenser, and being cooled down by a cooling system, where this cooling system had a pump. It pumps in cool water from river, lake, or ocean and cool down the steam. And the steam turn into water back, while the cooling system will flow out the warm water and repeat the cooling process. So the steam which turn into water will flow back to the container by another pump and repeats the process. So this is how nuclear reactor system works to generate electricity. Another method to generate nuclear energy is nuclear fusion. So it is the opposite process of nuclear fission, which is the process of fusing two nuclei to form a large nucleus. So for example, we combine hydrogen 2 and hydrogen 3. So after nuclear fusion, we'll form helium 4, a neutron, and release energy. The Sun and other stars release energy with nuclear fusion. The protons and neutrons in the nucleus of an atom are held together by very strong nuclear force. To have nuclear fusion to happen and release energy, protons and neutrons need to regroup into more tightly held arrangement than before. This can only be done in a very high temperatures and pressures to overcome the very strong force of electrostatic repulsion of the protons. Hence, here are the challenges to build a fusion reactor. The first is hydrogen must be heated to at least 40 million degrees Celsius and kept hot and compressed. Number 2. No ordinary container can hold one type of gas like this in extremely high temperature and high pressure. The possible solution is to trap the nuclei in a magnetic field. So since there are so many challenges to build a fusion reactor, what are the advantages to build a fusion reactor compared to fission reactor? Number 1, it can produce more energy per kilogram of fuel, hence it has high productivity. Number 2, hydrogen can be extracted from sea water, hence it is very low cost. Number 3, the waste product is helium, which is not radioactive. Therefore, it is clean and does not pollute the environment. Number 4, if the system fails, fusion stops. Hence, it is high safety. Lastly, let's talk about the use of radioactivity. First, for medical usage, it is used as tracers. Short half-life gamma emitters, example technetium-99m, are used as tracers. They concentrate in certain parts of the body that needs to be diagnosed. The half-life must be long enough for diagnostic procedures to be performed but short enough not to remain radioactive in the body for too long. Example, to check thyroid function. A patient will drink a liquid containing iodine 123, which will emit gamma ray. A detector will measure the activity of the tracer to find how it becomes concentrated in the thyroid gland. Another medical usage is to destroy tumors. Cobalt-60 can be used as gamma emitter to destroy tumors with a high dose of radiation. One more usage is sterilization of equipment. Gamma emitters are used to kill bacteria on equipment so that it is safe for infection when doctors perform operations on patients. In industry, radioactivity can be used as smoke detectors, and here is how it works. Long half-life alpha emitters are used in smoke detectors. Alpha radiation ionizes the air within the detector, creating a current. If smoke enters the detector, some alpha particles are absorbed and the current drop. Current detector detects the current drop and triggers the alarm. Another industry usage is thickness monitoring. Here is how it works. Long half-life beta particles are used to trace the thickness of metal sheet. So you can place beta emitter below the metal sheet and radiation detector above the metal sheet. As the metal sheet moves along the belt, beta particles are emitted and penetrate the metal sheet. If the material gets thicker, more particles are absorbed and less particles arrive and get detected by the detector. If the material gets thinner, less particles are absorbed, hence more particles arrive and get detected by the detector. Hence, adjustment can be done by the machine to keep the thickness of the metal sheet constant. Other usage, we can use it plant. By adding a tracer to the soil water, we can track a plant's uptake of fertilizer from the roots to the leaves. We can also detect leaks in underground pipes by adding a tracer to the fluid in the pipe. Artificial radioisotopes with short half-life are used for tracer purpose so that radiation is not detectable after a few days. Alright, that's all for this video. Thanks for watching and I hope you enjoy it. Do you have any question or doubts to ask? Feel free to write it down in the comment area. I would love to hear from you. Do you like this video? Please don't forget to like it and share it with your friends. Alternatively, you can also enroll this full revision course at Udemy. At Udemy, you can track your learning more effectively. Download my notes in printable PDF form. Take a summative quiz at the end of each chapter. Get your first-hand updated contents from me. Get quicker response from me, and many more. You can get all these benefits at a very affordable price. It is one-time payment, no recurring fees, no hidden costs. This saves you thousands of dollars on expensive tuition fees and revision crash courses. And most importantly, your precious time. Finally, you can do your revision anytime you like, anywhere you prefer. All is available within your fingertips. Check out the description below this video and click on the enrollment link to register the course at discounted price. Alright, until then, see you in the next video. Have a great day ahead.